Okay, so in this video, we're going to be talking about properties of determinants. Now, when we go and we calculate a determinant manually, using the cofactor expansion, we have to worry about the signs of the cofactors and the things that we're multiplying by, but we don't really engage in properties of determinants. But when we go and start using row operations to calculate a determinant, there are properties of determinants we have to keep in mind, that we have to keep track of, because row operations are going to potentially be able to change the value of the determinant. So if we make any of those changes, we then have to be able to back out of those changes using these properties. Now, these properties can also be applied when we know the determinant of a matrix and we do operations on matrices. So we're going to include those kind of properties as well in this discussion. So let's start with the row operations. So the row operations are basically that, so no change to the determinant if you add two rows of the matrix together. So let's say I have matrix A is going to be equal to, we'll just use a 2 by 2 example, so that we don't have as much typing to do, but it should illustrate the point for us. So our base matrix will just have entries A, B, C, D. So if I change the B matrix and make it equal to, let's say, A, B stays the same, but in the second row, I have C plus A and D plus B. So in the second row, I have added essentially row 1 plus row 2 and put it back in row 2, no change to the determinant. So if the determinant of A was equal to, say, 5, then the determinant of B is also equal to 5. So nothing has changed about the value of the determinant for A. And we could go through and we could prove this if we wanted to by actually calculating the 2 by 2 determinant for both of these examples. And we would see that everything cancels out and the expressions that we get at the end are exactly the same, which we could do. It's an example because it's only a 2 by 2. And this is a property that applies to matrices of any size. So if we were to try to prove this for the general case, for any n by n matrix, that proof would be much more difficult, but it would be easy to do for the 2 by 2 case without that much difficulty. You could also do it for, again, any individual size matrix if you wanted to do all the arithmetic. Now, it does matter exactly what you're doing when you do these adding two rows together. So if you, we're going to see, because if you multiply a row by something, that does affect the determinant. And normally when we do row operations, we combine this process of multiplying and adding. And so there are ways that can sometimes affect the determinant and sometimes not. But let's look at our individual operations. So if you multiply a row of the matrix by a scalar, you also multiply the determinant by the same scalar. So again, we'll start with my A matrix. Now let's say my C matrix, just so we don't confuse it with my B matrix, is going to be, and again, this applies to any row, A, B, 3C, 3D, then if the determinant of A is equal to 5, then the determinant of C is equal to 3 times 5, which is 15. So by multiplying a row, and again, it can be any row, of the matrix by a scalar, I have altered the determinant by that same scalar. Now, consequently, if I multiply the entire matrix by the scalar, then I have to account for that scaling factor on every row of the matrix. So we're going to see that later in some examples. So again, what is the row operation here? It's row 2, 3 row 2 goes to row 2. Now, when we combine these operations, it's going to matter where you do the multiplying and where you put your row operation back. So in combination, so let's think about 2 ways that we can combine this. Let's say I do row 1 plus 3 row 2 goes to row 1 versus row 1 plus 3 row 2 goes to row 2. These are going to have different results on the determinant. And the way that you can kind of think about what's going on is to think about what are the individual discrete operations you would have to do. If you could only do one thing at a time, not in combination, what would be the steps that would be involved? So in our first example, what we would have to do to put this result back in row 1 is what we're really doing. Again, if we can only do one operation at a time, is we would multiply row 2 by 3, then add to row 1, and then multiply row 2 by 1/3. Because in this operation, the row 2 is not changed when we're done with this operation. Row 2 is still itself. So what we've done, actually, we've needed 3 operations to perform this. We have multiplied by 3 in row 2, so that increases the value of our determinant by 3. Then we add our 2 rows together, which doesn't do anything. But then to get row 2 back to the way it was before, we then have to unscale, so to speak, row 2 so that it's back to the way it was at the beginning. So that affects the determinant by that 1/3 factor as well. And so the 3 and the 3rd cancel out. And so there's no net change to the value of the determinant. But in this operation, the steps are multiply row 2 by 3 and then add row 1. And that's it, because we are altering row 2. So we are not undoing that operation. We are still essentially keeping that multiplication by 3 in row 2, and therefore this alters the value of the determinant. This does not. So again, kind of keep this in mind when you're doing row operations, particularly when you're using row operations to calculate the value of a determinant. If you are careful about the way that you do your row operations, you can frequently avoid having to deal with your row operations further affecting your determinant. And only the ones that you scale deliberately are the ones that you will have to keep track of. Now, there is one other operation, and that is if you switch rows, you change the value of the determinant by -1. So by a scaling factor of -1, you flip the sign. So if we look back at our example, A is this, and then let's come up with another matrix. Switching the order would be C, D, A, B. So then if that A is equal to 5, then that D is equal to -5. So that switching alters the sign. And so recall this is row 1 with the double arrow, row 2. So this you will have to keep track of because this is always going to alter the determinant. So those are our 3 properties. So these are the things that you would want to keep in mind when you are going through and performing row operations to calculate the value of the determinant. If you can get it into triangular form, then you can just multiply along the diagonal, for example, or you can use your cofactor expansion to reduce the size of the matrix that you're working with once you get one column that is a constant and all zeros. You can simplify as you go. So these properties are very useful, but they also affect the entire matrix when we're calculating properties of determinants for matrices where we don't really have insight into the coefficients. Now, you will sometimes see questions about the values of the determinant simply from looking at like the result of a matrix or just row operations. So you could have an example like, suppose A is equal to, and we'll do a bigger one just for the example. So I've got A, B, C, D, E, F, G, H, I. And that A is equal to 7, then what is the value of B of det B if B equals and then they'll perform some row operation. So A, B, C, 3D plus G, 3E plus H, 3F plus I, and DEF. So the question then would be, so what row operations were used to obtain this matrix? So in this example, we would say that if I ignore the 3, D, E, and F, for example, there is a row switch to start with. So rows 2 and 3 were switched for each other. So that's going to be a -1 factor. And then the new row 3, row 3 was added to row 2, the new row 2. So because it's going back into row 2, that did not add an additional change. So what we can say is, therefore, det B should be equal to -7, and that's it. So we changed the sign because we flipped those 2 rows, But because we added a multiple of this row into a different row, that did not change the value of the determinant. If that second operation, if we had multiplied 3D, 3E, 3F in this bottom row, then that would have changed the value of the determinant. So that's that's a way that they can ask this. Another way is to ask what is the new determinant after a series of row operations are applied. And so they might give you, for instance, again, you know the value of your original determinant, and then they give you a set of row operations. And so you don't necessarily have to know what the values of the original entries are. You just have to know, is this a row operation that is going to change the value of the determinant? So are there some row switches? Are there some row operations like these where, which row am I putting it back into? And therefore, how is that altering the value of my determinant? Those are the kinds of things you just keep track of. What are the changes that are made with each of the operations, and then multiply those all together by the value of the original determinant to get back to that original, to get back to the new value of the determinant after those changes have been made. So those are some ways that those questions can be asked. Now, when we go on to just looking at the whole properties of the determinant, we can also incorporate these row operations, particularly the scaling, into our analysis. So consider one of the main ones that we need to worry about is the determinant of A, B, is equal to the determinant of A times the determinant of B. So again, assuming the operation is on square matrices, so they're both n by n, they're the same dimension, then we can apply this because we can calculate the determinant of A and B separately. If A and B are not square, then we can't do this. So doesn't make any sense anymore. But as long as A and B are both square and you can multiply them, then you can separate them out, calculate the two determinants separately, and that will give you the value of the determinant of their product. This implies that the determinant of BA is equal to the determinant of AB, because the determinants are real numbers. So the determinant of A and the determinant of B, I can switch the order, and that is what I would get when I multiplied use this same rule on the product of BA. I would get det B times det A, but that's the same because they're numbers now. I can flip them around. So these two determinants will be the same. So another thing we can again conclude from this, det A squared is going to be equal to det A times det A, which means the determinant of A squared is the determinant of A squared, quantity squared. So this also, again, you can see how this would apply. You could keep breaking this down into any power you want through a process of induction. The determinant of A cubed would be A squared times A. That'll get you the determinant of A quantity cubed, and so on and so forth. So the powers of the matrix are just going to raise the power of the determinant as well. And we talked about the scaling with the rows, so you can also write a rule for that. So the determinant of Ka, where K is a scalar, is equal to the number of rows of your matrix times det A. So this is something that's important to kind of keep in mind. because it depends on the size of your matrix. So if A is 4 by 4, and let's say det A equals 5, then the determinant of 3A is going to be 1, 3 for every row. So it'll be 3 to the 4th. Try this again, 3 to the 4th times 5. And 3 to the 4th is 81. And 81 times 5 is 405. If you don't know exactly how big the matrix is, you just know that it's n by n, that it's square, then you have to leave n as the number of rows in the solution. You can't really simplify it. But it does affect every row of the matrix. And so the impact that that scaling is going to have on the determinant of the matrix is going to depend on how big your matrix is. Same thing applies for -1. If you want to calculate a determinant of -A, if it's an even power, it's not going to have any effect on it at all. If it's an odd power, it's going to flip the sign because it's going to depend on the size of the matrix, how many rows are being affected. And so these properties can be tested, again, without having an actual matrix in front of you, just by asking questions about the properties. So for example, suppose that A is equal to -4 and that B is equal to 3. What is the determinant of the matrices below? So you might have something like det AB, which would just be -4 times 3, which would be -12. And what about det A squared? Well, that would be -4 squared, so that would be 16. What about det -2b? I didn't specify in the setup the number of rows, so this would be -2 to the n times 3, and I couldn't go any further than that. Now, one other thing that's useful is that the determinant of A inverse is equal to 1 over the determinant of A. And that has to be true. If you think about it, we know that A inverse A is equal to the identity, and the determinant of the identity is equal to 1 because the identity is just ones on the diagonal and zeros everywhere else. It's very easy to figure out what the determinant is. Well, we also know that the determinant of A inverse A is equal to the determinant of A inverse times the determinant of A, but we just said that's equal to 1, so we can solve for the determinant of A inverse. It's just the reciprocal. So again, this is something else we could ask as a question. What is the determinant of A inverse B? Well, the determinant of A inverse would be -1/4, and the determinant of B is 3. So the resulting product would have a determinant of -3/4. So these properties can all be applied sequentially and systematically in order to get you the determinant of any matrix, as long as you know what the determinant of the subsequent matrices are, the individual ones, you can scale them, you can multiply them, you can invert them, and you'll be able to calculate the resulting determinant of the new matrix product.